From the earliest days of rocketry, progress has always belonged to the scientists willing to think beyond the limit of their time. Long before rockets reached orbit, pioneers like Robert H. Goddard laid the mathematical and experimental foundations that proved spaceflight was even possible. And not long after, figures like Jack Parsons helped turn theory into raw explosive reality, building the propulsion systems that would eventually carry humanity beyond Earth. Today, we stand at a similar intersection point. Chemical rockets took us to the moon, but if humanity is going to reach the stars, we'll need ideas that once again sound impossible, until they aren't. In today's episode, we're exploring one of the most fantastical frontiers in modern physics, warp drive theory. Our guest is Harold Sonny White, a mechanical and aerospace engineer and applied physicist, and founder and CEO of Casimir. Join us as we get rebelliously curious. Sonny, thank you for joining me on Rebelliously Curious. It is great to see you again. You have been on this podcast once before talking about warp drive theory, so welcome back to the show.
Chrissy, yeah, thank you for having me back on. Thanks for the interest. Happy to have a conversation with you today. Always look forward to my conversations with you, Chrissy.
Oh, thank you, Sonny. I find warp drive it's so fantastical, right? I think space-time distortion, any of those theories that are really sci-fi based that, are sci-fi turning into science fact now it blows my mind. And some days I'm always shocked that I'm even having these conversations or other people are having these conversations and I'm living now in society and today and be able to watch these theories come to life. It's unbelievable.
Yeah, it's really cool. I grew up with Star Trek like a lot of kids. Wasn't quite with the first run of the series. It was a little. I watched it in syndication. It was on TV before I was born, but I got to watch it as a young kid, and just was really inspired by a lot of the things that I saw with the Star Trek the TV show in terms of the characters and the stories. Really kind of liked it. At the end of the day, it's not just about the things, right? It's about the people and the stories. And so, maybe another extension on this thought process is, I grew up in Washington, D.C. for much of my young life. And I got a chance to spend a lot of time in the National Air and Space Smithsonian in Washington, D.C. And the thing that was so inspirational walking through a place like that, you've got a lot of rockets and planes and landers and different things like that. And so while the individual things were interesting from a technical perspective, this plane went this fast and this plane went that far. When you spent any time looking at these things and considering the people that were involved in them and with them and the different challenges that they had to overcome to be able to achieve some of the things that are represented by what's on display in a place like that, right? It was very motivational and it definitely had a strong influence on me as a young kid. Always a bit technical, good at math. And so having that as additional, I guess, fuel for the fire, if you will, sent me down a path that eventually led me to, aerospace and working with airplanes and rockets and progressively going through the different perspectives. So yeah, it's always fun to daydream about space exploration. And then maybe the more salient question is, how do you get to these places, right? So.
Yeah, so true. How do you get to these places? I remember, I think it was about 2 years ago, I was in Ottawa and I went to the Aviation Museum and similar feelings in the way that you're saying, where I walked in and you're looking at one of the first planes ever created all the way up down to spaceships and then the Canadian arm, right? We're so well known in Canada for our robotics, especially space robotics. And I just walked in and I was like, oh my, like what? Like I just the feeling really does come over you. Like when you walk into a place of history or something that's filled with history, you can really feel it. And maybe not for everyone, but it does for me. And I just remember being at awe. And I was with my best friend Marie Nicola, and we were walking around, and we were doing some social media and talking about the aviation museum, but we were running down historically all different types of planes. But specifically when we got to World War II, I just
Mm.
stopped, and I was just like, from the design, how massive they were, to even how tiny some of these ships were that were like very explosive, like highly explosive ships, or sorry,
Mhm.
crafts. And then you
Mhm.
look at like the different types of design and artwork and painting and signs and images and symbols
Yeah.
that they had
Yeah.
on the planes to
Yeah.
represent how many missions they've done.
Yeah.
Dice, if like kind of like rolling your lucky dice and chance, I
Yeah.
believe.
Yeah.
So it was just an unbelievable experience to just be that close to something that really did change our lives, and especially my parents' lives. And my father, he's there, my background is German and Italian. And so,
Oh, cool.
knowing that and being in front of those planes and understanding how much it's changed our world and our lives now, and where we are today is an interesting point as well. But
Yeah, World War
yeah.
II, yeah, there was a lot of development in the aviation sector across World War II. You can kind of, as you look through the evolution and capabilities of aircraft across the decades, World War II was definitely connected to a very very big jump in capabilities over time for the obvious reasons, if you will. Interestingly enough, I think if I remember correctly, I don't know all my history, but I believe Gene Roddenberry was like a B-17 pilot in World War II, right? So he was connected with the U.S. I guess it'd be the Army Air Corps back then, and I think again I'm speculating. I don't know, but I think that some of the uh, maybe the motivation for the ship that's in the show that he created, the USS Enterprise, connects to some of the high regard that the U.S. military aircraft carrier, the Navy's USS Enterprise, the Big E, right, was a ship of note during the war. So sometimes it makes you wonder how those were connected.
Earlier in your career, you did work at NASA. Can we talk a little bit about what you did at NASA? Because you were doing warp drive theory, but I would imagine way before that, there has been a long lineage of you working at NASA and contributing to, space and space
Uh,
exploration.
Great question. Chrissy, can we do one small detour? I just want to add another piece from history.
Yeah, yeah.
Um, Speaking to the premise of rockets, Goddard is a person who's kind of considered the father of modern rocketry. He pioneered a lot of early rockets in the mid to late 1920s, and just such he was able to accomplish a lot of stuff at a very early period where a lot of people didn't even think this kind of stuff was useful or possible. But I just bring him up because a lot of people may not know, but in 1929, the New York Times wrote a an op-ed or produced an op-ed about Goddard's work. And in the paper where they were talking about his work with rockets, I'm gonna butcher the quote here, but it was along the lines of Goddard doesn't have the physics teaching that they give out in high schools every day across the country to understand that a rocket cannot be operated in the vacuum of space because it cannot conserve momentum. And so this was, an interesting about this by such a notable periodical such as the New York Times. And the New York Times, it took until I think a few days after the moon landing for the New York Times to issue an apology, an official apology to Goddard for that op-ed, right? So anyway, sorry, just an interesting history note since we're kind of
So wonderful. And it's just wild to think that so many people doing that type of work, you do have to think about your life, right?
mhm.
One simple mistake could cost your life or others. I think about that a lot when I'm thinking about anybody working on types of rockets or propulsion. It's a scary job and it's an intense job. I would
Hmm.
think. I would imagine that's changed now a little bit more. There's different types of safety, security, and regulations that go with this type of testing. But back then, you make one simple mistake and you're gone.
I think, that's a great narrative there. The amount of energy density associated with a rocket that's trying to, climb against the gravitational pull of the Earth and get to low Earth orbit, it's an enormous amount of energy density, and it has to process all of this energy to get to orbital altitude and orbital speed in a matter of minutes, if you will. So in this 10-minute kind of time frame, you're having to expend all of this energy. So if you kind of recast that into, well, what kind of power does that equate to, right? The amount of like the Falcon 9, the shuttle, any of these large rockets, if you go through and just do some back of the envelope calculations, the amount of power these systems are processing when they're climbing against the gravitational well to get to orbit, they're in the gigawatts power range, right? And so if you think about the grid in North America, it's in this 100-ish, 200-ish gigawatts of power. I think maybe at some of the when it starts to peak, if you will. And that's just electric power on the grid, if you will, just to kind of put that in context. And so when you see a rocket launch, you're basically taking an enormous amount of energy and trying to process it in a very short period of time. I've had some discussions with folks back when I used to do talks when I was at NASA, and the shuttle main engines, the turbo pumps, the liquid hydrogen turbo pumps on the shuttle main engines, they're LOX hydrogen chemical propulsion rockets. The turbo pumps on the shuttle main engines, they have, if you were to take a look at just some of the 1 inch by 1 inch blades that are on the turbines that are spinning, they generate so much horsepower that the average amount of power that's being processed by just that one little blade on the turbo pump is 900 horsepower, right? So in terms of trying to connect the dots with what you see to how that might relate to everything around us, it's just in a whole different category, right? Which is, I mean, that's where the whole premise of rocket science is hard. It's kind of born from that crucible of there's this challenge that we have to accomplish. We've got to lift this payload from the surface of the Earth and get it to low Earth orbit, and the solution has to look and feel a certain way, right? And so that's why it's such a daunting task, and you're motivated to rightly acknowledge the fact that it can be and has been a dangerous vocation, right? While in some cases we might take it for granted, it still doesn't change the nature of what you're doing when you actually lift something from the surface of the Earth and get to low Earth orbit.
When I look at even the Suicide Squad, Jack Parsons and JPL, I would think like what an intense man, practicing black magic on his day off or when he was done work, and then during the day he was blowing up things, and building rockets. And
Uh-huh.
it was just like such an intense life. And it's a specific person and personality type that does this type of work. I,
Uh-huh.
I truly believe that, you can't just be the average person doing this, that's for sure. And then you look at like historically, for so long, you look at all the different countries around the world from Germany, and all these different scientists speaking together, but nobody really believed the rocket scientists. They never thought that it could actually happen and that this could
Or
actually
that it would
be,
even be useful, right?
which
Why would we
is
why would we even
wild.
do it? It's there's so this gets into working in the space program. You get confronted a lot of times with the question, well, how does space really affect me, right? Why does it really matter to me? And if you kind of take a look at somebody's average day, the different things that they do. You wake up, maybe you go get a cup of coffee and you get a muffin. Depends upon your day, right? But if you think about just that piece of the day, when you're getting your coffee and your muffin, the ingredients that are in the muffin, like 75% of all farmland in North America is cultivated by GPS guided farm equipment or tractors or however you want to say it, right? So, very strong fingerprint of space in just that little aspect of that scenario I painted for you. Paying for the coffee, that's a global connected information network that allows the zeros and ones to process. So there's, space involved with that. If you check the weather, that's going to tie back to space assets. If you're driving to go see somebody, using your GPS guiding thing on your phone that's connected to space. So I think sometimes people don't realize how much space is already integrated into their lives. And then you add to that, now we've got Starlink, and Blue Origin is also going to be putting up their own network. And there are some other companies that are putting up networks that operate at operate large satellite constellations in low Earth orbit to provide data access in places that previously we couldn't get it. So yeah, space is definitely a lot more integrated into our daily lives, wherever you're at, whatever you're doing.
It's so true. It is. And we forget about that. We're
Hmm.
like, why do we need to fund this?
Hmm.
There's people that are, suffering, and there's people that need to be, fed on the planet. And I 100% agree with that. But there are reasons that why we have to contribute, because even those things, when it comes to GPS, different satellites, all of that stuff contributes back to society as well. So I agree. And we look at developing nations that are now using a lot more different telecommunications, right? And they'd be using those satellites when previously they didn't have any connection to, the Western world, let's say. So there's multiple reasons I agree that we have to look at investing into both and how they do work together simultaneously. Let's go back now to NASA and you previously working at NASA and what you did there as Sci, because I believe, correct me if I'm wrong, and near the end of your career, you were working in warp drive, but I believe that wasn't throughout your entire career, unless I'm wrong about that.
Right. Yeah. So I worked in the space program for the better part of 20 years. The first half of that was flight robotics. So I spent quite a bit of my time coming out to Toronto and hanging out in your neck of the woods with all of my friends, working with shuttle robotics and station robotics. Um, I got a chance to support human space flight. While we built the International Space Station, this is a great example that teamwork scales to the ultimate level, because this is a 500 metric ton spaceship that was built by all the nations on the Earth, if you will. But Chrissy, I've always been strongly interested in specifically advanced power and propulsion. Um, Most of my life, I've been driven by the question of what does it take to get human beings past Mars in the solar system? What does it take to get human beings to another star system, right? Two incredibly bold and challenging objectives. And so thinking about those types of questions for any length of time, it really helps you understand a few key things that you need in terms of advanced power and propulsion. And so I've been thinking across the kind of the full portfolio of different solutions for most of my life. And even while I was working flight robotics, I was interested in those types of topics and seeking out opportunities to engage with people at NASA and in industry to collaborate and work on different projects. And eventually, I was able to move from robotics into advanced power and propulsion at NASA and got to really focus exclusively on that. And so, you know, when you think about a challenge like, what if we want to send human beings to Saturn? This is an arbitrary thought experiment, Chrissy. What if we wanted to send human beings to Saturn and we want to get them there in 200 days? That's kind of a similar transit time to what we've always considered okay for a Mars mission. So if you just kind of map that duration to a farther out destination, And then you calculate the amount of energy, delta V, that's necessary to achieve that type of objective. You rapidly come to the conclusion that chemical propulsion, that's kind of the backbone of all the stuff we just talked about earlier, these things that we use to get from the surface of the Earth to low Earth orbit, they don't have the right type of performance, and they never will have the right type of performance to enable that kind of emission. It will, if you do the calculations, it won't even close. The delta V for something like that is like 150 kilometers a second of energy. Whereas getting a payload from the surface of the Earth to low Earth orbit, it's about just under 10 kilometers a second. So it's an order of magnitude more energy that's necessary to make that mission work. And so, if you can't use chemical propulsion, then what could you use? And so, I think that's kind of the background that has fed my journey as I've moved through working at NASA and eventually moving on beyond NASA. And so I think about a lot of different things that fit into a taxonomy of advanced power and propulsion. And of course, space warps and warp drives is kind of the end point of that, if you will. But there's a fun Neapolitan ice cream list of topics for us to kind of unpack if you want to unpack that a little bit today.
Yeah, it'd be really wonderful to see a video breakdown of that historically, like how we started from chemical, and looking at different types of rockets and propulsion, and then to where the future could look like, right? And how, and a just kind of, yeah, like a historical breakdown timeline done through animation would be very interesting, right? Or done through AI. Most
Yeah,
people would hope yeah.
It's great that you mentioned that. I think you're familiar with one of our products that we're associated with. There's a short video called "Go Incredibly Fast." We pulled that together back when I was at Limitless Space Institute, the nonprofit that I left NASA to help stand up. And the video "Go Incredibly Fast" it's kind of like an emotional story, if you will, that kind of tells a very technical story, but in a way that connects with a lot of different people so that maybe they can help better understand things. But it covers a spectrum of techniques that we could potentially leverage to allow us to accomplish some of these awesome deep space mission objectives, like sending humans to Saturn or any place in the solar system, and then maybe even onto another star system. And so the way it presents the solutions we can potentially leverage is it starts from what we know from a physics and engineering perspective, and then works its way to the frontiers of both physics and engineering in terms of what we don't know. So it starts with, in the context of known physics, known engineering, nuclear electric propulsion. So, Chrissy, this is a scenario where you've got a spacecraft that has a nuclear reactor that is fissioning uranium, like any nuclear reactor we might think of as a power source. And so this is providing electric power that then feeds into some form of electric propulsion. And we can talk about that more in just a second, but something that's using electromagnetic fields to ionize and accelerate a propellant to generate a force. And so nuclear electric propulsion as a capability, I apologize, I have a Teams meeting that's trying to come up, so I'm not texting anybody. Hold on, let me just
It's okay.
get rid of this message that just popped up. Nuclear electric propulsion, known physics, known engineering. This is a capability, right? If I put on my old NASA mission planner cap and I've got a bag of systems that I'm looking at as the capability, if I pull out some Lego bricks that say nuclear electric propulsion and I put that into an architecture, and then I try and consider what I could use that for, that type of power and propulsion element allows us to send human beings to every destination in the solar system. It has the capability to do those much larger delta V missions. And that's known physics and known engineering. So
the evolution I find to be so fascinating, right? And I think that if you want to expand a little bit more about, the theories that you've had when it comes to jumping off the Kubrick theory, right? When we look at warp drive, and I believe there's been multiple different patents. I think the Kubrick theory is one of the theories, but I believe NASA had two previously patents, or there's two other people that worked at NASA, from what I remember. When I was reading Christopher Plain's original articles he wrote for the debrief about warp drive theory, that historically there were, and then there was the Kubrick theory. But then you've taken the Kubrick theory and have built off that. And now we're sitting with a secondary, I would say, theory that you've come forward with that looks at it potentially being practical within more of a larger practical scale world at one point in time.
Right. So the idea of a space warp is in that's presented in that video, and that definitely traces to the frontiers of what we know, both in the context of engineering and physics. So when you start to think about the premise of an interstellar mission, and you might ask a question of, well, how might we get to another star system in a time frame that we can kind of relate to, like a year, let's say. What if we want to go to Proxima Centauri and we want to get there in a year? That's just an objective we want to state. The first thing that comes to mind is physics tells us there is a cosmic speed limit. General relativity sets the cosmic speed limit as being the speed of light. And so that would tell us that if we need to adhere to that constraint, we cannot go to any destination faster than the speed of light in the conventional sense. However, general relativity as a framework provides a couple of loopholes that we can utilize to try and go somewhere really quickly. And one of those loopholes is the idea of a wormhole, and the other is the idea of a space warp. And the idea of a space warp is kind of born from the premise that although there's this cosmic speed limit, thou shalt not exceed the speed of light, if you will, you can expand and contract space at any speed. There's no speed limit whatsoever at which space can expand and contract. And we know when we look at the cosmos, at the very early moments of the cosmos after the Big Bang, there was an inflationary period where if you were to imagine 2 points that are close to one another in the very early cosmos, right after the Big Bang, you pick a couple points and you stand on one and you watch the other, you'll find that the other point will move away from you with such a speed that's like 10 to the 30th power, right? A big number times the speed of light. So we know through astrophysics and cosmology and through observation, we know that space can indeed expand and contract at any speed. And we have evidence for that when we look at the early portions of the cosmos. And so this type of realization served as fuel for Alcubierre's thought process when he was kind of trying to merge the ideas that he saw in Star Trek and the things that he was learning about general relativity. How can I take what I know from this mathematical framework and maybe bring a solution that looks like what I think and see in this TV show? And so he published a paper in 1994 that kind of captured that idea of a space warp in a physical form. And so if you think about the idea of the Alcubierre metric in the form that he presented in his paper, there's a lot of things you can look up online, but I'll try and describe it with words. It's kind of like a bubble type warp bubble that gets formed as a result of creating a toroidal ring of exotic matter. So you create this toroidal ring of exotic matter, or it's like if you imagine you've got this little football shaped central portion, maybe the crew lives there, and then you've got this toroidal ring that's attached to it, and it moves in a direction such that it's orthogonal to the orientation of the ring. And so the ring has to be filled with something in general relativity we call exotic matter. And so that's the physical form that Alcubierre's model takes when you kind of map the math into some physical form. And so the cool thing about what he did, right, is he was able to kind of go through and explore what he understood about general relativity in the mathematical framework, and using some specialized approaches, he was able to develop this concise, encapsulated model that expressed the idea of a space warp in mathematical formalism. And so, great achievement for him. It served as things that uh, inspire folks to think and do their own stuff. And that's kind of was my entry into the idea of space warp, was becoming aware and familiar with Alcubierre's paper from 1994. And so I got into the game a little shortly thereafter, around 2003. So,
Yeah, it's fascinating. And the work that you did previous to the recent paper that came out and the article that I wrote at the debrief, you were working in a lab as well. And so, people are like, there's a warp bubble that's been created, right? And we looked at this from, it wasn't like a full warp bubble on large scale, right? Can you talk a little bit about the original work that came out and that really did put you on the map?
right. So the paper that we published in so you're talking about the paper that we published in Neurophysics Journal C in 2021. And so that had to do with some nanostructures that we were working on. So we were working on developing some power generating nanotechnology under a DARPA contract. And so we were working on some customized Casimir cavity geometries. And so in the process of studying how the quantum vacuum responds to the little structures that we were making, when we looked at the predicted energy density distribution in and around the custom structure that we were making, it looked qualitatively very similar to a two-dimensional section cut of the energy density distribution for the Alcubierre warp metric. And so we looked at it a little bit and said, well, wow, it's close, but it's not exactly right. But what if we tweaked the structure a little bit and made it a little different from our custom Casimir cavities? And instead, I'm going to use hand props here. Hold on. What if we had a scenario where we had a 1 micrometer diameter sphere, NASA golf ball. We had a 1 micrometer diameter sphere, and we put it inside a 4 micrometer diameter cylinder, right? And then if we study how the quantum vacuum is predicted to respond to this more complicated three-dimensional topological shape, it will manifest a negative vacuum energy density around this structure so that it is predicted to manifest a real nanoscale warp bubble. And so the paper that we published allowed us to say to the broader community, we can now propose a real structure that we can go 3D print with a nanoscribe GT printer that prints down to those levels I just talked about, and then do some electrolysis plating and metallize the whole surface. And it is predicted to interact with the quantum field in such a way that it will generate a real nanoscale warp bubble. Now, it's not going to, as we said in the paper, it's not going to go anywhere. It's not going to do anything. It's a static warp bubble, but it's going to have optical properties. And so that might be an interesting initial empirical thing that could be explored. Maybe you can make these things in mass and then pass a photon through some kind of apparatus, if you will, and see if you can see some changes in the optical properties, some phase shifts induced into the wavefront as a result of passing through this sequence of little warp bubbles put one right after another, like pearls on a chain, if you will. And so that was the significance of the paper that we published in 2021. We were able to say to the broader community, for the first time, there is a real structure that we can make with things that we have at our disposal that's predicted to manifest a real warp bubble. And we can go through and explore the optical properties of that warp bubble. Now, the forward work, right? In the paper, we say this is forward work. Somebody's got to go figure out what's the experiment, how big of a signal, can we detect it, right? The other aspects that need to be looked at. So
It's unbelievable. Like it just blows my mind.
It was a lot of fun, that was for sure.
Oh, I can
And
imagine. And even just being able to publish that, it's so exciting. And also just to be in the forefront of that type of work, right? And laying the ground for the next
uh,
people that will come and build something into a larger scale. Like, so exciting.
yeah, that was the cool thing about that is Chrissy, we didn't go into that with the objective of trying to figure out if we build this type of a structure at the scale I was talking about. We weren't doing that kind of work. We were building, these little custom Casimir cavities with the express purpose of trying to generate power for other low power applications we were interested in. And that just happened to be a happy coincidence or happy accident, however you want to articulate it. But it was, in my mind, it's one of those things that you never know when innovation opportunities are going to strike like that. And so, but we wouldn't have figured that out if we weren't doing the other research, right? So.
It's true. And now the new paper that has recently come out, you talk about, and I'm going to butcher this, nacelle. I know nacelle is basically
Nacelles,
talks about
yes, nacelles, yes.
nacelles based
Yeah,
geometry. Can you
yeah.
talk a little bit about that paper? And I believe that is more of the paper was looking about how this could be used in more of a practical use in context of geometry that we use today, right?
Uh, yeah, so you and I talked just a little bit before we kicked off, and nacelles, the origin of that term, right? I worked commercial aircraft before I got involved in human space flight, and so I worked on 737, 777s, all the full family of Boeing aircraft, commercial aircraft. And so the engines that you see on commercial aircraft, right, those are called nacelles. So when you go to Boeing in Wichita, Kansas, there's a whole building that's called strut and nacelles, right? So the struts that hold the engines in place and the engines are called nacelles. And so I think even in the TV show, they used the word nacelles for the engines that were on the Enterprise, but it actually comes from the aviation industry first. And so, but that's where the term nacelles comes from. In terms of the paper that we published in Classical and Quantum Gravitation, a new model that goes through and considers some topologies where instead of having the toroidal ring of negative vacuum energy density around the portion that might contain the crew, we looked at scenarios where we would have nacelles, cylindrical assemblies, nacelles arrayed in a cylindrical pattern around where maybe the central portion of the spacecraft might be. And so the purpose of the paper was to see, can we construct a model that is consistent in the context of general relativity that allows us to place these individual nacelles, whether it's two, three, four, it could be more. We even looked at doing one. Can you generate a warp bubble? Can you have a negative vacuum energy density distribution or exotic matter distribution that generates a warp bubble that would allow you to accomplish the things we talk about with the Alcubierre metric. And so it provides a very different framework for you to go through and construct a warp bubble. And by doing it that way, instead of having just a large ball, you can now have extended cylinders, if you will. So you can optimize the spacecraft in different ways. The spatial gradients that you might have on the end caps could potentially be a little different. So some of the concerns associated with in terms of how it focuses radiation as a result of its spherical topology through the center of the warp bubble, the nacelle model potentially allows you a different way to set up the warp bubble so that you can spread out that radiation and minimize the damage that it could potentially cause. So lots of new opportunities with that. But I think maybe the other parenthetical thing is now you can construct something that looks a little bit more like what we saw in the TV shows, right, where they have nacelles, if you will. So interesting to think that artists just being guided by their intuition, like the piece of art that's behind you, right? Artists just guided by what they're thinking and what they're feeling as they go through and they craft what they envision this stuff might look like. It's sure fascinating to think how close to correct some of their speculations were, right? So,
It's wild and subconsciously too.
right, right.
Are there any boundaries or just are there any challenges that you're having right now outside of the science? Is there political challenges that you're having? Is there administration kind of challenges that you're having, doing this type of work? Are there roadblocks that you have to get over consistently with, certain type of advocacy groups or just different types of people in the science community as well?
In terms of the scientific community, right? The most important thing that we can do is to try and do very rigorous work and put together very meticulous and detailed papers, and go ahead and put yourself through the peer review process. Take the time, interact with your fellow scientists, take the feedback and the criticism and look at it. Did we miss something? Should we sharpen this here or change this narrative or what have you? And so, the peer review process is a little bit longer than what some people might want, but it still serves a very important purpose in the community, and it allows us a mechanism where we can go through and put new ideas out there. But we put them through a crucible, right? And so, a new idea that you have, you give it to other people that are interested in talking about these things, but they'll give you good, solid feedback. And the end result is, while it takes longer, and sometimes it's a lot of comments that you get. The end result is you get a solid paper, right? And so it serves as the next node in the roadmap that allows the progression of ideas and thinking. So, yeah, I think it's very worth the time and effort. It looks like you have a question, and I want to delta to a different topic related to this, but let me pause and give you the microphone.
I was thinking about just the relationships that people had when we're looking at, past rocket propulsion programs and how people were connecting all over the world and how scientists were talking to each other, even though historically, even though politically or even just within the science community, they thought, this is never going to happen. Rockets are never going to happen. But people in Germany were talking to Americans and people were speaking all over the world, and scientists were sharing information or just talking about where they were at. Do we see that today in your line of work? Are we seeing this cross connection? I would imagine that obviously you're funded, so people are funding this because it's important, it's pushing science forward. But is there that international collaboration that we've seen in the past? Is that happening now?
Right. Thank you for a little bit more narrative there. That was very helpful. I'm gonna use that to calibrate something. So, I worked at NASA for 20 years, left NASA to go help stand up Limitless Space Institute, where we got some support from Limitless Space Institute, but we were also funded by DARPA Defense Science Office. But DARPA Defense Science Office did not fund space warps. While I'm sure individuals at DARPA may have interest in that, that was not DARPA was not funding a space warp. They were funding the development of nanotechnology in this case, with an eye towards power applications. And so the work that we were doing for DARPA on the power generating nanotechnology that we were working on, customized Casimir cavities, we got a lot further with that work than we anticipated. And so it became very relevant that we needed to stand up a commercial company and try and commercialize this power generating nanotechnology. And so I left Limitless Space Institute to go stand up a commercial company, spin out a commercial company called Casimir. And so Casimir is the commercial company that we are using to try and commercialize our power generating nanotechnology. And so, although our market entry, our beachhead market for our technology, I'm gonna hold up this is a little platter full of chips, some of the prototypes that we made at one of the universities nearby that we work with. Sorry, get it a little bit better centered there. These are actual prototypes. They have many tens of thousands of these little customized Casimir cavities. And so we test these chips in dark RF shielded enclosures to study their performance over time. And so they generate voltage and current. And so part of our initial market application for these things are low power electronics. Think tire pressure monitor system, something that's in your car, a key fob, a remote control, an Apple AirTag. I could go on. There's just a very large array of low power electronics. And so, although it might not be obvious that coming up with a persistent power source for a tire pressure monitor system would have anything to do with bold deep space exploration or even space warps, but it turns out it has everything to do with that, right? Part of what we do with these little custom Casimir cavities is we are trying to create special distributions of negative vacuum energy density that causes preferential flow of electrons from one portion of the structure to the other, and in that way provide power. And so as we continue to develop these products and our understanding of things, all this knowledge and insight helps better calibrate some things that we might think about when we think about the idea of one day of a space war. And so the the problems that we're trying to solve right now are very terrestrial and by comparison probably mundane by anyone's account, but they are still absolutely of critical importance in terms of the understanding that they bring that helps us continue to spiral around spiral our knowledge continually up to where we want to eventually get to. So
For sure. Well, and I imagine it's a progression, right? It's going to take time, and you're going to see all these different evolutions. I would go back then to just the international collaboration. We look at potentially China or other countries that might be working on warp drive technology. Have you heard of any of these other countries that might be our competitors, that might be foreign adversaries that potentially could be? We look at China, and I bring them up because I'm fascinated by China consistently and the technology, them in a space race with us, even though maybe people don't consider we're in a space race, but we really are. And just looking at all of the amazing technology and how close they are to cracking, quantum, right? And when we look at different comparisons, people are saying, I wrote this article from an open debate program that I did watch, and was talking about all different people from different sectors within government and science and technology, but they were debating if China is more advanced than we are. And what the conclusion kind of was that nobody really knew, but what they thought and what they've heard, and I don't know how you would ever really evaluate this, is that the States was only 3 months ahead of China. And so to me, that was kind of, well, how do you really know that? No, and at the end of it, no one really does know, right? It's so hard to get that intel from China. But when it comes to warp drive tech, have you heard of anything that maybe China or other countries are working on that's kind of similar to what's happening in the States?
Yeah, the only thing that I could speak to would be Limitless Space Institute. We funded university through our grants and fellowships program. We funded universities all across the globe that wanted to do work in advanced power and propulsion. So we put out 2 solicitations for 2 biennial 2-year research cycles and funded a bunch of universities that worked on advanced power and propulsion concepts. And so part of that family of grants that we funded, some were connected to the idea of space warps and wormholes. Those were predominantly theoretical only, right? So it's just mathematics. They were not doing anything in the lab. They weren't at the state where they could do that. We did fund some other grants that were working on trying to understand from an experimental sense some of the characteristics of the quantum vacuum and the quantum field, if you will, putting it into things that start to look like applications, not a space warp, but still trying to figure out if there were some applications that could bring value to some of the problems we're confronted with as a society today. And so I think that would be the only thing that I could really point to where I could give you evidence that, hey, here's some people that did this, or there's a public briefing here, they published some papers. And so I could point you to those types of things. To my understanding, I don't think anybody is probably working on the idea of a space war. A lot of people might say different. I'm just not aware of anything that traces to that zip code. Should be great if somebody showed up at my office with a notebook and said, "Hey, we got a lot of good information in here. We want to make sure you got it right." So if anybody's got one of those, send them my way. I'll put it to
For
good
sure.
use.
And if they're working on it,
Yeah,
they're
yeah.
listening and watching. That's for sure. If they're,
Fair enough. Yeah.
and that's what they would be doing. They would be quietly probably watching until the one day they're able to release what their findings are. Sonny, thank you so much for being rebelliously curious with me today. The work that you're doing is just so fantastical. And, it blows my mind to know that we're even this close to potentially maybe one, in my lifetime, maybe by the end of my lifetime, but being able to see this become something that's practical. And it would change humanity forever. And I think it's just being someone that's contributing to that must be such a wonderful feeling.
It's definitely provides a lot of fulfillment. And I'll if you don't mind, I'll finish with this. When it comes to space exploration, once once we develop a capability, right? Yeah, this gets into the whole why space exploration, why go to the outer solar system, why go to other star systems. When we as a species develop a tool, a capability, right? We figure out all the ways that we can put that tool or that capability to good use to help improve our conditions around us. We don't have to have philosophical discussions about it. We just do it, right? This is just how we are. And so I would imagine that as we build advanced power and propulsion capabilities in their many and varied forms, ranging from nuclear electric propulsion, fusion propulsion, and space warps, as we build these capabilities, we will use them to the fullest extent that we can. And so in terms of why space exploration, it's like, well, as soon as we build these capabilities, they're going to be using them anyway. So we really don't need to get too lost in the philosophical discussion. Furthermore, I would propose that having an entire solar system worth of resources and the advanced power and propulsion systems necessary to go to those places, by definition, we're changing the premise of scarcity for everybody, right? So
It's very true. And it will change humanity forever, you know.
mhm.
So
in a
thank
good
you
in a
so
good way, right?
and
So
yes, I agree too. I'm very optimistic in that. I'm very optimistic that space exploration and science are, you know, there's such a negative connotation sometimes within the science community, or not around the science community, I should say.
mm,
But I think very optimistic. I think that's the only thing that we have that will push humanity forward in a positive
mm,
way. So maybe we
mm.
should get rid of politics first, and then we let science rule.
Right,
But
right, right. That'll
anyway,
do. Yeah, that'll do right there. So
exactly. Thank you, Sonny.
sure. See
That
you,
was
Chrissy.
great. Thank you.